तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
Yeah, so what's the question?
The question which I asked in the mail.
Uh-huh.
I have read one article which is from American Journal of Physics. In that article, he says that there is a close classical analog of the spin. He says that spin is equivalent to the angular momentum of a polarized electromagnetic wave, circularly polarized electromagnetic wave. But in the class, you mentioned that this is a purely quantum mechanical concept, something to be associated intrinsically with that particle and no classical analog. So, is that a contradiction?
Okay, good question. It's a deep question, and the answer is in several parts. The statement I made was that spin was not like orbital angular momentum, which has a classical counterpart, but rather some kind of intrinsic angular momentum intrinsic to elementary particles. On the other hand, it's been pointed out that spin is like the states of polarization of electromagnetic waves, and since electromagnetic waves have classical counterparts, we see classical electromagnetic waves. Is there not a contradiction? Doesn't it mean that spin is also a classical object? There is a classical counterpart to it. Okay. Now it's a valid question, and the answer goes in several parts as follows. First of all, we believe that elementary particles really are the fundamental constituents of matter and radiation. We believe that quantum mechanics and relativity really are the guiding principles for understanding all of nature. Okay. Then it turns out that once you accept quantum mechanics, everything is quantized. Elementary particles which you see around you are really the quanta of some field or the other. The electron is a quantum of the electron field, so to speak. The proton is a quantum of its own field. Actually, it turns out today we understand that nucleons like protons and neutrons are themselves made of quarks which have their own fields. In the same sense, photons are the quanta of the electromagnetic field. So even though the electromagnetic field appears to be a classical object, the fact is it too is quantum mechanical. It requires the right kind of experiments to probe its quantum mechanical nature, and it turns out that radiation too is in the form of quanta, but these quanta of radiation are slightly different from the quanta of radiation, the quanta of matter like quarks or electrons and so on. The difference lies in the fact that the quanta of radiation have zero rest mass. On the other hand, the quanta of the electron field or the quark field and so on have finite rest masses. The relation between the energy and momentum of a zero rest mass particle is different from that for a massive particle, and this difference all of you know. So on the one hand you have E squared is C squared P squared plus M squared C4, on the other hand you have E equal to Cp when M equal to 0. This is a linear relation, that is not a linear relation at all. This leads to a lot of differences in properties. That is point number 1. Number 2, we have said that every elementary particle, when you impose the requirements of special relativity, the wave function of these elementary particles would be characterized or labeled by two quantum numbers, quote unquote quantum numbers, two labels, two eigenvalues of certain generators of the Lorentz group, because you require these wave functions to transform in a specific manner under Lorentz transformations. so that the laws of physics can remain form invariant under Lorentz transformations. And these two labels, if you like, they come from the values of certain generators, certain operators which induce transformations, certain operators belonging to the inhomogeneous Lorentz group, which commute with all the generators of these groups of the Lorentz group. Those two operators are the following. First of all, when I say the inhomogeneous Lorentz group, I mean that translations in space and time, namely shifts of the origin and shifts of time, are permitted, and there are 4 generators for it, which are denoted by P mu. The 0 component here corresponds to the energy or the Hamiltonian, and the 3 spatial components correspond to the linear momentum. And then you have rotations in space, rotations of the axes, and velocity transformations. So there are 4 generators here, and then rotations of the coordinate system are specified in 3 dimensions by 3 possible Euler angles, and therefore there are 3 parameters there, and then you can also have velocity transformations in any directions, in any direction whatsoever, and there are therefore 3 velocity components specifying an arbitrary Lorentz transformation or boost from a frame at rest to a moving frame. So those are induced by a set of 6 generators. Mu and nu run over the value 0, 1, 2, 3, and this is antisymmetric in mu and nu, and a 2 by 2 tensor in 4 dimensions has 16 components, but if it is antisymmetric the diagonal ones are 0, that leaves 12 components, and they are equal in magnitude, opposite things on the opposite sides of the principal diagonal are negatives of each other. So there are 6 independent generators here. 3 of these correspond to rotations and 3 more correspond to velocity transformations or boosts. Together these 10 parameters, these 10 generators form a 10 parameter group. They generate a 10 parameter group called the inhomogeneous Lorentz group, and our belief is that the laws of physics are form invariant under such transformations in flat space time. Now these generators also lead to 2 combinations of these quantities which commute with all of these generators, and those combinations are P mu, and the other one is a little more intricate. You start by defining a vector W mu, which is epsilon mu nu sigma rho P nu j sigma rho. These are all contracted indices which are repeated are contracted, and they are written upstairs and downstairs for technical reasons which I will not go into now, because these are Lorentz transformations in 3 plus 1 dimensions, and this is a 4-dimensional vector. Once again it is called the Pauli-Lubansky vector, and this quantity W mu is also an invariant. This operator commutes with all these generators, and so does this. Therefore the wave functions are labeled, the irreducible representations of the Lorentz group are labeled by the numerical values of these quantities, and this guy here in suitable units turns out to be m squared or m squared c squared. Let me put c equal to 1 for the time being. So this is what leads to the rest mass of a quantum, of a particle. This guy here on the other hand does something interesting. This thing here is a scalar, and you can ask what its value is in the rest frame of a particle, and that turns out to be proportional to m squared s times s plus 1. These are all proportional to, depends on the units. So this s here which comes out is the intrinsic angular momentum quantum number of a quantum, and then of course the rest of whatever I said about angular momentum follows. So this is the origin of spin and mass for a particle. But now you could ask, what does this become when m is 0, because it just looks like it goes to 0. That is where the difference comes between a particle with 0 rest mass and one without 0 rest mass. This turns out to be proportional to the component of the spin in the direction of the linear momentum of the particle, because a particle with 0 rest mass always moves with the speed of light. If you stop it, it is annihilated, that is it. So free photons always moving with the speed of light, the fundamental velocity, and this thing here turns out to be S dot P over S P if you like, where these are the magnitudes of these vectors. So you can get rid of this, it is just a normalization factor, it is the component of the spin along the linear momentum of the particle, and it is called the helicity of the particle. Now if you took an object with spin S, spin quantum number S, and asked what are the possible values of S dot P divided by modulus P, then it is like asking what are the possible values of a single projection of the spin operator along any direction, and there are 2s plus 1 such values, because Sz or S dot n or S dot any unit vector has 2s plus 1 values when you apply quantum mechanics. So this thing here would have 2s plus 1 values. Since I have normalized by S, these values would run between -1 and +1. If I do not have this, they would run from -s to +s in steps of unity. So now coming to an electron, since S is half, you only have the values -half and +half. On the other hand, if you look at an object with spin 1 for instance, like a photon, then S is 1 for a photon, you would expect therefore that this quantity would have 3 possible values, -1, 0 and +1. However, because it has 0 rest mass, the definition of this vector, this object is different in the case m equal to 0 not equal to 0. This object here itself can only have 2 values whenever m is 0, that is the way it works out, and this becomes equal to ±1 when m equal to 0. Okay. +1 you would call one helicity, -1 you would call the other helicity. Okay. Now comes the connection between what happens classically and what happens quantum mechanically. A photon has S equal to 1, but it has rest mass equal to 0, therefore it does not have the Sz equal to 0 projection. Sz or S dot P can only be +1 or -1, and that is the connection with classical states of polarization. Left circularly polarized light corresponds to S equal to 1 and Sz equal to 1 or helicity equal to +1, and right circularly polarized light corresponds to helicity -1. So there is still an intrinsic angular momentum, and it does arise from the spin of the photon. So I would go the other way and say the states of polarization of radiation arise ultimately from the polarization of the photon, from the spin of the photon, the spin quantum number of the photon. Only these two are possible. You don't have S equal to Sz equal to 0 projection at all. Now that is true for every spin 0 particle, every mass 0 particle. It is believed that gravitation is carried by the graviton. You have not seen it, people are hunting for it, there are problems with it, but if it exists it would have spin S equal to 2. Therefore 2s plus 1 would be 5. You would expect 5 possible projections or 5 possible eigenvalues of S in the helicity. You do not have 5, you have only 2 once again, plus or minus 1, that is it, after you divide by the 2 there for the S. Now what is the reason why you could see this polarization classically? That is buried in yet another subtlety. The fact is, when a particle has integer values of its spin quantum number, then a collection of such identical particles obeys Bose statistics. When it is half odd integer, a collection of identical particles obeys Fermi-Dirac statistics, and this implies in Bose statistics it turns out that you put a collection of identical bosons together, there is no restriction on how many of these bosons you can put in a given state. In the case of fermions there is a restriction which is called the Pauli principle, which follows actually from the spin statistics connection, from consistent quantization, that you cannot put more than one such particle in any given state at a given time. Okay. Since photons are bosons, there is no problem with putting a large number of them in exactly the same state. In particular, there is no problem with putting a large number of them in the same polarization state. Therefore you can observe a classical polarized beam of light, because a whole lot of photons are contributing to the same state. This is also the reason why both gravitation as well as electromagnetism got observed long ago. Gravitation got observed long ago, right? When the first ape fell down from the tree, gravity was observed. The reason is again just this, these are classical fields, they are long range fields, they are massless. Now whenever forces are caused by 0 rest mass particles being exchanged, the corresponding force is a 1 over r force in 3 dimensions, potential in 3 dimensions, and that is long range. Otherwise if there is a rest mass associated with the particle, then the corresponding force is proportional to e to the minus mu r over r, where mu is the reciprocal of the Compton wavelength of the particle, and it depends therefore on the mass. If mass is 0, you just get a 1 over r for the potential. This is what happens in the case of electromagnetism and gravitation, but in more complicated cases where particles with mass are exchanged, then in the non-relativistic limit, in the static limit, etc., you end up with a potential of this kind. So this is why if you had massive particle exchange, those forces would be very short range, and that is the reason why weak interactions are very short range. They too are mediated, radioactive decay is another word for weak interactions, they too are mediated by particles, by bosons which have spin 1, but they are massive, and because of that the range is 10 to the minus 15 centimeters, 10 to the minus whatever 18 meters or whatever or less, and this is the reason why you do not see it classically. The same is true in the case of the strong force which holds these which binds the quarks together into nucleons. These nuclear forces too are extremely short range, the reason being that the forces are mediated by particles which are bosons, which have spin 1, but which are massive, and therefore the range becomes short. So even though there is a potential for these things to become classical and so on, you do not see it in real life. So there are two effects playing a role here, one is the mass of these exchange particles and the other is actually the statistics they obey. Now you could have 0 rest mass fermions in principle. It was believed for a long while that neutrinos were massless and are fermions, spin half. So you could ask, can I not have a force mediated by neutrinos which would be long range and so on and so forth, but the fact is you cannot have a classical field of neutrinos. The reason is that you cannot have more than one of them put in the same state. You need large numbers of large quantum numbers to observe it. Okay. Now the final point, all angular momentum is quantized. The angular momentum of the ceiling fans is quantized, but like I pointed out, the quantum number is so large that the discreteness does not play a role at all. On the other hand, when you come to elementary particles and you have something like S times h cross, and S is of the order of 1 or 2 and h cross in our units is 10 to the minus 34, you see that as far as comparison with daily life angular momenta is concerned, this is completely negligible, but the quantum effects become very, very significant. Okay. Now having said all that, let me also say that if you took the classical theory of fields, not quantum mechanics, did not impose quantum mechanics, only relativity, and you looked at what these fields did, then the moment you have more than one component to the fields, multi-component fields like vectors, tensors, spinors and so on, then it is possible, it is necessary in fact to introduce the concept of an angular momentum carried by this field, even though it is a classical field. In that sense this is a classical analog of spin, it is at a deeper level, this is still a classical analog of spin. So it is not possible to have a consistent classical relativistic field theory of a tensor field for example without introducing the idea that this field actually carries angular momentum, but that is also true for the electromagnetic field. The electromagnetic field carries an angular momentum, the classical electromagnetic field carries an angular momentum, but the origin of that angular momentum when you go deep into it is due to the spin of the photons finally. So in that sense there is no classical versus quantum divide. The classical mechanics is a limiting case of quantum mechanics and everything ultimately has a quantum origin. So I hope that kind of explains this confusion. I mean people could write these, so this is classical, that is quantum, this is I look at classical physics as a limiting case of quantum mechanics, okay, a very essential limiting case, necessary, it is needed for interpretation and so on and so forth, but the fact is that we believe that the fundamental laws are quantum mechanical. Yeah, pardon me, yeah, off topic, okay.
Maybe carry it out after the class.
Okay, good, yeah.
Sometimes another question.
Mhm.
Probably, okay, sir. Is our space quantized in the sense that given a
Okay,
quantum?
now we're getting into deep waters. Is the space-time quantized and so on. We will come back to this at some stage, more opportune moment. Okay. Anything else? Okay. Then let's get back to what we were discussing. We had stopped last time at the radial equation. I need to point out some features of this radial equation. So to quickly recapitulate, our Hamiltonian is p squared over 2m plus v of r, which we wrote in the form pr squared over 2m plus l squared over 2m r squared plus v of r. It was an arbitrary central potential. We made some assumptions, and the Schrodinger equation we wanted to solve was minus h cross squared over 2m del squared phi of r plus v of r phi of r plus phi of r, and we discovered that this phi of r could be written in the form r of little r, and then the angular part was characterized by the spherical harmonic YLM, the normalized spherical harmonics, and this radial quantity r of r, if I wrote it in the form u of r over r, then there was a convenient radial equation for this quantity here, which was d2u over dr2 plus 2m over h cross squared times E minus v of r to m r squared. That was the centrifugal barrier on u equal to 0. And the boundary condition we required was the following. In order to make this whole thing respectable, we made the assumption that r squared v of r equal to 0 as r tends to 0, so it is not too singular at the origin. Then the boundary conditions were u at r equal to 0 was 0, and we required it to be normalized such that mod u squared dr less than infinity. So this means u must go to 0 sufficiently rapidly. The r squared in the phase space factor was taken care of by this division here, and we want it to be 0 at the origin. Okay. Now this has become a one dimensional problem. Now what can the energy levels depend on? Well, first of all, the angular part of the wave function is completely determined by this, and it is specified by two quantum numbers L and M. Therefore any state of the system that I am talking about already has two quantum numbers in it, L and M, and for given values of those quantum numbers we are going to examine this and ask does it have solutions and so on. What we did discover was that what we see immediately was that the effective potential is V of r plus a repulsive 1 over r squared potential, which we call the centrifugal barrier. And we also know that even if there are bound states supported, these bound states are going to get a little less tightly bound as soon as L starts becoming larger and larger due to the centrifugal barrier. The question even arises whether for a given potential you may have a bound state or not, because if this becomes arbitrarily large it could stop the potential from having a minimum at all, it could become too shallow. So at once you begin to see the possibility that in 3 dimensions, because of the presence of this centrifugal barrier so to speak, the number of bound states that are possible is actually going to be restricted. And you could even ask, for a given value of L and a given potential, is there a bound on the number of bound states you could have, and the answer yes, there are such bounds. Okay. Now what would the wave function depend on? It would depend on the value of E, the eigenvalue of E. We have to solve this eigenvalue equation subject to these conditions, and of course the value of L and possibly on M2. But from this equation it is immediately clear there is no M dependence here at all. M has completely disappeared from this equation, the quantum number M, not the mass, the quantum number M has completely disappeared from this equation. That at once shows that in a central force problem no single axis is distinguished from anything else. That is why there can be no dependence on M at all, which is the quantum analog of the classical statement that in a central force problem you have symmetry about all axes, you have spherical symmetry, and therefore there is no particular axis singled out. The energy eigenvalues E therefore cannot be functions of M. Now what can it be a function of? What will it depend on? That depends on what V of r is. Okay. It will turn out this is a one dimensional problem, so we could use our knowledge of what happens in one dimension. We know that in one dimension A there is no degeneracy, and B the wave functions are ordered in such a way that the ground state has no nodes, the first excited state has one node, the second excited state has two nodes, and so on. The same thing is applicable here, except that it is as if you have a line in which you have an infinite barrier to the left of r equal to 0, because we have imposed the boundary condition that u is 0 at r equal to 0. So this is like a half line problem, some potential on the right hand side which may support bound states, and on the left you have an infinite barrier. Then the ground state has no nodes excluding r equal to 0, which is a boundary point, and then the first state has one node, and so on, exactly like a particle in a box from 0 to L. The ground state was sin pi x over L, which was 0 at the endpoints by boundary conditions, but no node in between. The first excited state had exactly one node, and so on. So I expect the same thing to happen here, and therefore I expect that this E would be a function of two quantum numbers, one of which would be n radial. There would be a radial quantum number which would label, run from 0, 1, 2, 3, etc., and label the energy eigenvalues of this one dimensional problem for a given value of L, and of course if I change L, this would also once again change the energies. So therefore I expect that these energy eigenvalues will be a function of some radial quantum number and the L quantum number, but not M, This is what we expect to start with. Yeah, now we need to now examine and ask, for a given value of L, are there bound states at all possible or not? I have to solve, I have to find out, are there normalizable solutions at all, etc. Let us first settle what happens at the origin. Let us first look at that. Now in order to make sure that we do not run into technical difficulties, I have assumed that V of r does not go like 1 over r squared, but slower than 1 over r squared. When it does go like 1 over r squared, then we have to re-examine the problem, and I will do that very briefly, but let us put this assumption in and ask what happens here. What kind of physics do I expect? I expect here is r, here is V of r. A typical potential which would support bound states would be, there is a barrier here, so to the left of this the potential is infinite, and then on the right hand side I expect something, maybe a well like this, maybe this would have some bound states, possibly, maybe a well like this is gone off 0 as a function of r, maybe a well like that, that is a shape, and so on. Even the harmonic oscillator, even the 3-dimensional oscillator, so here is r, here is V of r, which is just r squared. This is an infinite well in which you could have only bound states. Okay. So these are the possible kinds of shapes that I am thinking of. Notice that you also have the possibility of a Coulomb potential, which is V of r, which is like this, it is like a 1 over r with a minus sign of course. Okay. This also could have bound states, and it does, as you can. So it is this kind of problem that I am trying to address at the moment. Well, let us first settle what the possible behavior of u of r can be near the origin. We have said we will impose the boundary condition u equal to 0 at the origin, but what kind of solutions come out from this equation? Well, let us look at that equation here. Near r equal to 0, this is some finite number hopefully. If V of r does not go to 0 as fast does not explode as fast as 1 over r squared, then the dominant term near r equal to 0 is just this term here. And then you have to solve an equation which says near r equal to 0 u double prime is like 1 over r squared times u, because that is what this eigenvalue equation tells me. Okay. Now that is a simple equation to solve. A simple way of solving it is to assume that u is a trial solution of the form u is some power of r. So let us u r to the s implies s times s minus 1 u to the s minus 2 r to the s minus 2. I differentiate it twice, and that goes like on the other side it is in fact L times L plus 1 over r squared. So this is an exact equation sufficiently close to the origin. So this is L times L plus 1 u to the s r to the s minus 2, which implies s times s minus 1 is L times L plus 1, and the solutions are obvious. So it immediately implies that u of r goes like r to the power L plus 1, because s is L plus 1, therefore s minus 1 is L. Or r of r goes like r to the power L, because r of r is u of r over r. But there is another possibility, it is a second order differential equation, so you must have two linearly independent equations solutions, and the other equation is, the other solution is u of r goes like r to the power. So the other solution is implies s equal to L plus 1 or s equal to minus L. That is possible too. So this is minus L, this is minus L minus 1, that minus signs cancel and you end up with this. So this is r to the minus L but that is not a regular solution, that violates our boundary condition. Even at L equal to 0 it violates the boundary condition. You would like u to vanish, okay. Pardon me? It violates the solution, so it is not physically acceptable. You see, I have a differential equation but I also have a boundary condition, and those are the physically acceptable solutions. Just as if I give you a differential equation you may have non-normalizable solutions, but the physically acceptable wave function is a normalizable one. So this solution is not acceptable. It is not that it does not play any role whatsoever, the fact is this is only near r equal to 0. There are always two linearly independent solutions to this equation, to the general equation, and the general solution is a superposition of the two, okay. But you have to also satisfy the boundary conditions. So this is the physically acceptable solution, and this incidentally answers the question of what is the actual behavior of u near the origin. The behavior is u goes like r to the L plus 1. So in the ground state u goes like, when if L is 0 in the S state, u really goes like r, and this fellow goes like a constant. So that is our first lesson, okay. In fact you could do something better. You could say, suppose v of r was 0, I am looking at free particle motion in spherical polar coordinates, what would it look like, okay. Normally it would depend on the initial state. If I have an initial plane wave state, then of course I must expand that plane wave in spherical waves and then look at what happens to each one of these. That happens in scattering theory. Right now I am worried about bound states here. So if you have no potential at all you can't support any bound states anyway, okay. But it tells us that if you had this equation, then if the potential behaves sufficiently well near the origin, then this is the way the wave function, the physically acceptable wave function behaves near the origin, okay. So you managed to extract that piece of information. Okay. Now you could look at different classes of potentials. For example, let us look at a thing like this. Suppose this is some minus V naught and it is a well till the point A and 0 after that. One could put that in here and say B of r is minus a constant V naught till r equal to A, and after that it is 0, and ask what do the solutions in this thing look like, what normalizable solutions look like. Now what would the wave function look like as a function of r? What should the wave function look like in this region? It should clearly die down exponentially, otherwise you can't normalize it, and in this thing it could be oscillatory out here, and this is the problem of a particle in a spherical well, because now you have said u equal to the potential V equal to 0 till a certain radial distance, and after that it is completely 0, and it is an attractive potential. So it turns out, yes, you can solve this problem. I am going to give it as a problem and tell you to show that you can, if the well depth is sufficiently large, have a bound state. Unlike the one dimensional case where no matter what the well depth was, as long as it had a finite depth and width, you always had at least one bound state, the ground state, and then you may or may not have had excited states. In this problem in 3 dimensions, it turns out that you need to have a sufficiently deep well in order to have a bound state, otherwise it is not going to work, because it is a 3 dimensional problem. And then if the well is deep enough, you may have an excited state and so on and so forth. Okay. Our interest now is really to look at the problem, the Kepler problem, the 1 over r, the Coulomb problem, and let me explain where that comes from, what happens there. If this quantity is equal to minus Ze squared by r for the hydrogen atom, then one is faced with the task of solving this equation explicitly, and there are changes of variables which lead you to an equation for a special function called the Laguerre function, and one can solve this equation completely, put it back and write down the exact solutions. I am not going to go through that here, it is a standard piece of algebra in textbooks, but it turns out in that case that the energy levels E for the 1 over r potentials, so 1 over r okay, it turns out that the energy levels E are functions of the following combination. They are functions of only n since this radial quantum number goes 0, 1, 2, 3, as I said earlier, L goes 0, 1, 2, 3, n itself goes 1, 2, 3, etc., and is called, as you know, the principal quantum number, and E of n, En, goes like minus 1 over n squared in suitable units. Okay. There is no explicit L dependence. This is an accident. This is not an accident, it is a consequence of the fact that the potential is 1 over r, it has extra symmetries. It is not true for a general central potential for which the energy eigenvalues are functions of 2 quantum numbers, but in this special case it can be reduced to single combination. This is called accidental degeneracy, and as I said on several earlier occasions, it is a peculiarity of the Coulomb problem. I will in a very short while tell you where this extra symmetry is. N therefore is 1, 2, 3, 4, pardon me, NR is 0, 1, 2, 3, etc., and now if you work it out and requires square integrability, etc., then not only is n 1, 2, 3 all the way to infinity, but L runs 0, 1, 2 up to n minus 1. So as all of you know, this leads to the counting of the degeneracy of a hydrogen atom state. When the principal quantum number is n, then the possible number of states, independent, linearly independent states corresponding to this quantum number n have to be summed, have to be computed by summing over from m equal to minus L to plus L, summation L equal to 0 to n minus 1, and when you include spin, then the electron can have two possible spin projections along any direction, and therefore there is an extra factor 2, and it is a trivial exercise to show that this is equal to 2n squared. This is 2l plus 1, and summation L equal to 0 to n minus 1 of 2l plus 1 is n squared, and when you multiply by 2 you get 2n squared. Okay. So this is what happens in the case of the hydrogen atom. We will come in a minute to what the reason for this extra degeneracy is, but I emphasize once again, except for these problems with special symmetry, and there are just two of them. One of them is this 1 over r potential, and the other is the 3-dimensional harmonic oscillator, this potential. Except for these two, in general for a central potential the energy will depend on the orbital angular momentum quantum number as well. Okay. That degeneracy is not lifted. No dependence on m, the magnetic quantum number m, for any central potential, that is due to spherical symmetry, but there is a dependence on L. Okay. What happens in the case of the harmonic oscillator? Let us do that also quickly. This Hamiltonian, this V of r equal to 1/2 m omega squared r squared. Now that problem is very easy to solve. In fact, we do not need to go to spherical polar coordinates at all, because r squared is just x squared plus y squared plus z squared, and del squared in Cartesian coordinates is just the second derivatives with respect to each of the Cartesian coordinates, the second derivatives, and the problem separates in Cartesian coordinates, and we know what the solutions are for the one dimensional oscillator, and now you simply have to multiply it by the corresponding wave functions in y and z. So for the 3D oscillator it is very easy to find phi as a function of x, y, z. It is trivial to find. And what are the solutions? Let us put all these quantities equal to 1 or something, and let us write down what the solutions are. So here is my Hamiltonian, it is px squared plus py squared plus pz squared over 2m plus half m omega squared x squared plus y squared plus z squared. Then it is completely trivial to write these solutions down, because we know that in one dimension the solution would be e to the minus x squared over 2 in units of square root of m omega over h cross square root of h cross over m omega. So let us put all those factors in hn of x, and then a normalization constant. This is the wave function, and n runs 0, 1, 2, 3. Now what do you think is a wave function in 3 dimensions? Since it is separated, since it is solved by separation of variables in Cartesian coordinates, it is just a product. Therefore the actual wave function phi as a function of x, y, z would be equal to some normalization constant multiplied by e to the minus x squared plus y squared plus z squared over 2 hn of x, hn of y, hn of z, except that for each degree of freedom you need a quantum number. So it is n1, n2, n3. This c would be a function of n1, n2, n3 of course. That is what the solution is. What are the energy eigenvalues, and therefore this is labelled by 3 quantum numbers n1, n2, n3, and what are the energy eigenvalues? E as a function of n1, n2, n3 equal to h cross omega over 2 h cross omega times n1 plus n2 plus n3 plus 3 halves h cross. Each degree of freedom gives a 0 point contribution half h cross omega, and for 3 dimensions you have 3 halves. What are the allowed values of n1, n2, n3? 0, 1, 2, 3, etc. So you could write this as n equal to n1 plus n2 plus n3, and then you have En equal to n plus 3 halves. What is the degeneracy of the state n? It is the number of ways in which you can write a non-negative integer n as a sum of 3 non-negative integers n1, n2, n3, and what is that? What is that? It is not nc2. So the ground state is 0, 0, 0. Yeah?
Plus 2c2.
Yeah, n plus 2 c2. So Gn the ground state is just 0, 0, 0. All 3 quantum numbers must be 0. Capital N equal to 1 can be done in little n equal to 1 can be done in 3 ways: 1, 0, 0, 0, 1, 0, and 0, 0, 1, and so on, right. So you have n oranges and you got to put them in 3 boxes. You need 2 partitions. So actually you have n plus 2 objects and you can permute them as you like. The number of permutations is n plus 2 factorial, but the two partitions can be permuted among themselves, which is 2 factorial, and the objects can be permuted among themselves, n factorial. So when you divide n plus 2 factorial over n factorial 2 factorial, you get that. So that is the degeneracy of the state, and the wave functions of course would depend on n1, n2, n3, and the ground state has no node at all. It is just a Gaussian e to the minus r squared, as you would expect. So this is it in Cartesian coordinates. Now what would happen if you solve the same problem in spherical polar coordinates? I can still do that. I should get exactly the same answer. Then I go through this L, M, etc., and it will turn out the energy values are exactly the same, but once again in this case it turns out that E equal to En does not depend on L, does not depend on M, once again in this problem too, but here L runs 0, 2, 4 for n even, 1, 3, 5 and on. It can run all the way up to n. So if you work this out, this is what happens. I leave it to you as a trivial exercise to show that if you sum 2L plus 1 over these allowed values of L, then indeed you end up with that degeneracy there, not 2n squared, not n squared, but this quantity here. But again this problem has this has an extra symmetry, exactly as the Kepler problem has. Now what is the reason why the Kepler problem has this extra symmetry? We saw in classical mechanics that a particle making an orbit or under the moving under the influence of a 1 over r potential, in addition to the angular momentum, it has another constant of the motion, another vector constant of the motion, the Laplace-Runge-Lenz vector, and that carries through in quantum mechanics too. Classically the potential minus so V of r go to minus k over some constant over r. This vector classically was equal to P cross L, yeah, minus m k r over r, which is equal to this, and this quantity is constant where L is the orbital angular momentum r cross p. And just to refresh your memory, if the classical orbit was like this in an ellipse with one of the foci being the center of attraction, then the direction of this vector must be constant in time, so you can evaluate it at any instant of time. In particular, if you evaluate it at this instant of time, it is easy to see that it is along this direction, because at that instant of time the momentum is perpendicular to the radius vector, okay, and then it is easy to see that it is actually along the r direction itself. So the direction of the semi major axis, and this direction does not change, which means the ellipse does not precess, and that is a characteristic of bound motion in the 1 over r potential. Quantum mechanically this would be an operator, but it has to be a Hermitian operator. It is made up of observables. Is this Hermitian as it stands? R of course is a Hermitian operator, no problem there. P is 1, L is 1, so is this a Hermitian operator? P and L do not commute with each other. L is r cross P, so there is an r part inside L and that will not commute with P. So this is not a Hermitian operator. How should I fix it? What should I do to this? Minus. I use this, okay, and then indeed you can show that this commutes with the Hamiltonian, and the presence of this extra symmetry, this extra constant of the motion, leads to this accidental degeneracy. Actually that is not a very satisfactory way of saying it. You could ask, okay, I have another constant of the motion, so why should I have an extra symmetry here? For this I have to take you back to classical mechanics and recall to you that you actually have the Hamiltonian remains invariant and the equations of motion remain invariant under a group of transformations which have to be canonical, so that they are symplectic transformations and they do not change the structure of Hamilton's equations, and the Hamiltonian has to remain invariant. So you look at that subgroup of the symplectic group sp6 in this case, which keeps the Hamiltonian invariant, and therefore the set of solutions goes to the set of solutions, and that subgroup for this hydrogen atom, for this Kepler problem is SO4. It has 6 generators and they are formed by linear combinations of A and L. So this is the role played by A and L. They act, or the linear combinations act, as generators of infinitesimal transformations under which the Hamiltonian as well as the equations of motion do not change in phase space. So that is what constants of the motion like this do. Similarly, in the case of the harmonic oscillator, this oscillator, there are a large number of symmetries, there are a large number of constants of the motion here, not all functionally independent of each other, but there is a symmetry group. The 3-dimensional dynamical symmetry group happens to be SU3. It has 8 generators and they can be formed from these combinations. Actually it turns out that this combination here, Pi Pj plus Qi Qj, where Ij runs over 1 2 3, they are actually constants of the motion. Of course you put I equal to j and sum over I, that gives you just the Hamiltonian itself, that is one of them, but that tensor of rank 2 is a symmetric tensor actually is a constant of the motion in suitable units. The angular momentum of course is a constant of the motion. So qi pj minus pj qi, there are 3 of these combinations, they are also constants of the motion, and they together form a complicated algebra, and the algebra happens to be that of SU3. So that is the reason why that problem has a degeneracy. Quantum mechanically you can write down the corresponding expressions for these generators, they commute to the Hamiltonian and you expect this extra symmetry. But there is one more way in which you can predict when a problem would have this kind of symmetry, and that is when the Schrödinger equation is separable in more than one coordinate system. This sort of tells you that there is some symmetry. This Hamiltonian is separable in 2 coordinate systems. What are they? Clearly Cartesian and spherical polar coordinates. Therefore you expect a certain degeneracy here. The hydrogen atom problem is not separable in Cartesian coordinates, because this 1 over r is bad news in Cartesian coordinates, so 1 over square root of x squared plus y squared plus z squared, but this problem is separable in spherical polar coordinates and what are called parabolic cylindrical coordinates. So there are 2 coordinate systems under which they are separable, and then you have this symmetry. Incidentally, if you had just free particle motion, just del squared in the Hamiltonian, which is p squared if you like, then there are 11 in 3 dimensions, there are 11 orthogonal curvilinear coordinate systems in which del squared is separable. So potentially you would expect, if you had no potential at all, you would expect that in these 11 coordinate systems you would have some special features or symmetries, but the moment you put in a potential V of r, that is gone automatically. Now of course we know from classical physics too that the r squared and the 1 over r are the only 2 central potentials for which all bounded motion is closed orbits, they are all closed, and that carries through to quantum mechanics too. So both the oscillator and the Kepler potential are very, very special, they are the 2 solvable cases, they are also the 2 important cases. As I pointed out, even later, even further on in relativistic quantum physics and field theory, the 1 over r potential plays a very, very special role. Okay. It is intrinsic to nature itself for a variety of reasons. Okay. So I have not solved these problems in a very tedious way, but the solutions are available in textbooks so that you have exact expressions for the wave functions, but I thought I would give you some idea of why these solutions look the way they do, and that is more or less where I would like to stop. What we need to do now is to ask what happens if the problem is not exactly integrable. What happens if I give you an arbitrary Hamiltonian and it is no guarantee at all that I can solve the Schrödinger equation. Then I would try to do it by what are called perturbation or approximation methods of various kinds, of which perturbation theory is very crucial, and I would like to introduce that. The other point is, very often you have a quantum system and you do something to it out from outside, you apply a time dependent perturbation and then it induces transitions between the levels of the system. That comes under the purview of time dependent perturbation theory. So I would like to introduce in this course at least the rudiments of both time independent and time dependent perturbation theory. There are simple rules, including a famous one called Fermi's golden rule, which I would like to definitely talk about, because that is absolutely crucial to applying quantum mechanics anywhere. And then after that, the very last topic we will talk about is what I have been mentioning throughout, namely the spin statistics collections of identical particles, and this will help us to terminate the course. Okay, so until next week.